Last time we saw that ABB can be expressed as a determinant, right? So with W depth D ABP, this can be written as a determinant of a matrix of size of the dimension WDN, and is the number of variables in F. And the proof was very simple. It was just converting. So you are given an ABP with source vertex S, destination vertex T. You are every path from S to T. That contribution you get by a cycle. So give a reverse edge from T to S of weight 1, and that will make a path into a cycle. So every path becomes a cycle, and together with that cycle you can also use the self loops to look at it as a cycle cover. So every path actually corresponds to a cycle cover, and that gives you the determinant by this combinatorial interpretation of determinant. Any questions? So now we'll come to the more interesting part, which is the converse. So we now want to convert determinant into an ABP, and this will actually improve algorithms of determinant that we have seen till now. So determinant we'll show has a width n square, depth or length n ABP. And all we will use is commutativity of the entries in the matrix. So what will be the algorithmic implication of this? Well, this will actually mean that determinant is again in VP, as which we have already shown, but the depth will be better. So depth will only be log n now. Depth will be log n, and this will be a completely uniform way. You will get a fast algorithm to also compute this representation given an n. Okay, so the advantage is that the depth is now log n in contrast to log square n that we saw using the other method, using Newton identities. One point of difference is that now the fan-in will be unbounded. So depth will be log n, but in contrast to the other, the older circuit where depth was log square n and fan in fan out was 2, here we are making the fan in fan out arbitrary, so it will be bounded by the size of the circuit only, and reducing the depth to log n, and this cannot be improved any further. Okay, we don't expect this to be improved at all. So this really gives you an optimal result for determinant computation using parallel algorithms. So if you want a fast parallel method to compute determinant, this is the implementation to be used. Okay, this is a unique result. We don't have anything better than this.
What is the relation with parallel algorithms before each path or something?
No, so every addition multiplication gate should be seen as a chip, so or it's simply a microprocessor. So if you have these, let's say size, if the size of the circuit is n to the 4, so for size to compute size and determinant, you pay the price of manufacturing these n to the 4 many microprocessors, and then whatever input matrix is given, n cross n matrix, the time to compute the determinant is only log n. Okay, so the parallel complexity, time complexity is only log n for this n cross n determinant.
All of them work simultaneously.
Yeah, so they are working simultaneously, yes. The microprocessors are actually working in parallel, but their time will not add up. The physical time which you will see will only be the length of the path. Yeah, and theoretically this is a nice result because it shows now equivalence of ABP model with the symbolic determinant model. Okay, these two models are the same. So determinant is something unarguably it is fundamental, and we are getting this model to be equivalent to this new model which we had defined, ABP, and this we have defined in a completely different way. Still they are equivalent, right? So that is a nice theoretical result. So how do you show this, right? How do you convert determinant into an ABP? So determinant is defined, we saw the combinatorial interpretation using cycle covers. So you would want to convert or implement cycle cover as a path now, right? And this does not seem easy or even possible. So yeah, it will be a non-trivial, it will be a complicated proof. So what we will do is we will actually prove something more about determinant, more properties of determinants. The main tool in the proof is a relaxation of disjoint cycles which appear in a cyclic cover to closed walks. While still computing determinant. So we had in the cycle cover we use disjoint cycles, of course. We want to relax it to closed walks. So the difference would be that now you will be allowed to actually repeat vertices. Okay, these will not be simple cycles, and moreover across. So in the case of cyclic cover, across cycles the vertices were disjoint. That will also be false now. So across these closed walks, vertices may actually be repeating. Okay.
The same cycle won't repeat again.
Yeah, so all kinds of repetitions are allowed now. Within a closed walk, you can repeat a vertex, and across closed walks, also you can repeat vertices. So there will be only one thing which you won't be able to repeat, and that is called head of the walk. So we would want heads to be distinct. So let us now define this formally. So let G be a graph on vertex set 1 to n. So what we will call closed walk. So a closed walk or a clo of G is a clo is a closed walk of length L so it will have vertices V1, V2, VL, and then it comes back to V1. Okay, so it is a closed walk, but the vertices other than V1 may be repeating. with V1 being unique and minimum. So it's the unique minimum here. Okay, so we are thinking of the vertex set as numbers 1, 2, 3 dot dot n. So there is an ordering, and a closed walk is just you are basically walking in a sequence of vertices. So obviously V1 to V2 there should be an edge, and then V2 to V3 there should be an edge. So you are taking you are picking these edges, walking along them, but so everything is allowed except you should not fall below V1. Okay, so V2 to VL, all of these should be strictly bigger than V1. So that is the only constraint. Everything else you are allowed to do. So this designated vertex is called head. So call head of C to be this set to be this vertex V1, or define head of C as V1. So head doesn't repeat. Okay, that's the thing to remember. It doesn't repeat as in it doesn't repeat in the middle. When you are repeating it, the closed walk ends. The walk closes. Okay, so the walk gets closed at the point you come back to the head. Any questions? So that is one closed walk. So this is a relaxation of a cycle. Now, to get a cover, you want to look at a sequence of closed walks with increasing heads. Okay, so a closed sequence is a closed tuple. So a tuple of close or a collection of close C1 to CR with increasing heads. That is, head of C1 is less than head of C2 dot dot head of CR. Okay, so this is they are distinct and in increasing order. Yeah, note that here we are not putting the extra condition of covering all the vertices. So they may be missing some vertices, but it won't be important. For the final result, this covering will not be important. So just think of this closed sequence as a set of closed walks. Closed heads are strictly increasing. Within a close, you are allowed to do whatever you want. Just respect the head. Any questions? Okay.
So there, when we were doing, the reason we were able to find that connection was because cycle covers are very close linked with permutation.
Sure.
Is there something?
Yeah, sure. This will also give you determinant. That is the observation by, well, invention and observation by Mahajan Vinay.
I mean, right now, is there any link between flow and?
Yes, so cycle covers, a cycle cover is a closed sequence. That's the connection.
Okay, but it's not the other way around, right?
Well, so for that we give it a sign. Okay, so for that we first define length. So the length of a closed sequence is the sum of the lengths of the underlying close. So naturally it is just these vertices which you are seeing. So in a close you will see vertices V1 back to V1. Yeah, and then sum it up over all the close in the sequence. And then the sign of a close sequence should be, what do you want to define the sign as? Minus, so parity of some number, right? Which should be the length. Well, okay, not the length. So you have to, again, you have to define it analogous to cycle covers. So in the case when you are looking at a cycle, when your close sequence is a cycle cover, what is the sign? Number of even cycles, right? So this should be parity of number of even close to be consistent. So this is inspired from the sign of cycle covers. Yeah, otherwise there is really no motivation why you should look at the parity of even close, number of even close, just to be consistent with cycle cover. We define it like this, and now what will happen is that these close sequences which are not cycle covers, in the sum we want them to cancel out, and this is what we will show, that they indeed cancel out with the sign. Okay, that's it. Once we have shown that, we will have the connection with determinant. So let us just recall also the weight definition. So the weight of a close sequence, this should be the product of weights of the underlying edges. Yeah, so length of a claw I think is then number of edges you see, not the vertices. The number of edges, which was also the case in cycle cover. And weight is just you take the product of these edge labels. Okay, that would be the weight. So every claw gives you a signed weight. Every claw sequence you will just multiply these to get a signed weight for the claw sequence. And
weights that we take the product of, we take it only once if it, or as many times as
oh no, you repeat it.
repeat it.
Yeah, if an edge repeats, you have to multiply. The idea is that it will not matter because there will be a close sequence of opposite sign with the same weight, so they will cancel anyways. Okay, cancellation is the magic here.
It's not bounded, right? The length of a close sequence.
Yeah, that is a good point. Yes. So is it bounded? The length of the number of claws is bounded because the heads have to increase, and within a claw, does the definition allow doing this infinitely many times?
I mean, you cannot do it infinitely. I mean,
You can do
you can do it arbitrarily.
Arbitrarily, no.
Arbitrarily long, yeah.
But then, yeah.
Yeah, so the definition as it stands seems to suggest that you can do this infinitely many times. So I guess no, in the end, I think we'll just put a bound on this. So do not. Yeah, we have to see in the implementation, but there will be a bound. So we will not be doing this infinitely many times. Within a claw, just a natural bound, say more than n or n square, is what is where we'll stop. Within a claw sequence, the number of heads cannot be more than n, and within a claw also you don't have to look at all these arbitrarily long claws. Yeah, it will be clear from the implementation when we'll want to compute it. But for now, let me just continue with more observations. So first simple observation is that a cycle cover is obviously a closed sequence. Of the same weight and sign. That is by design. Right, so this should be clear. Just compare the definitions. And so the surprising thing is that this sum will also give you determinant. So Mahajan Vinay, that paper shows this lemma that if A is the adjacency matrix of a graph G, then determinant of A is equal to signed weight of a closed sequence over all the closed sequences. In the graph G. Okay, so the attraction here is this equality, right? You know that determinant is equal to this sum if you went over all the C's that are cycle covers that we had seen before. Now we are saying that even if you relax cycle cover to a closed sequence, the sum is the same. It doesn't add anything. In other words, so to prove this, it is equivalent to proving that C's that are not cycle covers, they will cancel out.
So again, like he pointed out, if you did not put that bound, this sum wouldn't be a finite sum anymore, right?
Right. Yes.
You just loop around and create another.
Exactly. Yeah. So once you have a cycle, you can just keep repeating it. Sure. So we will see that in the implementation. So for now, just think of a very large upper bound. We'll exactly see what that is. Yeah, I think it will simply be n. The ABP which we will construct will be of depth n, and it will just use n edges, not more than that. So the idea is that you should be able to cover, subsume all the cycle covers. And if you think of a cycle cover, there how many edges do you see? You see only n edges. So you restrict your closed sequence close to be just n. In fact, the closed sequence you restrict to be n. You don't need to go above that, because within that you will be able to subsume any possible cycle cover, and the rest of the things will be produced with in different ways with different sign, and they will cancel out. So n will be the correct bound. So maybe I mention it here. So length will be less than equal to n. Just we are putting that restriction, but you can take it to be any bound bigger than n, doesn't matter. Just for finiteness we put that bound. Okay, right. So the thing we will show is exactly that. We will show cancellation of bad close. So key idea is the contributions of closed sequences that are not cycle, they cancel out. This cancellation we have to show. Yeah, usually showing this cancellation is I mean, in a complicated computational model, showing cancellation is highly non-trivial. Here it will be made easy because we'll actually show that if you look at a cycle cover with a sign that is, you look at a closed sequence with a sign that is not a cycle cover, then by a simple manipulation you can get another closed sequence with opposite sign.
Which is in this one.
Yeah, it will be in this sum because it will be a very simple manipulation. We'll just take two close, either we will join them or we will break a claw into two claws. Okay, so either join or break. So this will change the parity.
If we're joining, then this length restriction is a bit iffy, right?
No, but those edges were already there. Joining means, so the length is not changing.
So it's just like a union.
Yeah, the length is not changing, but the sign is. The sign will change.
But the sign depends on the length, right?
No, it depends on number of even claws.
It's still a bit iffy. Even though
So we'll see it in the proof, and then we'll also see in the implementation.
edges are allowed to repeat, you could have length less than n, but still only say length n, but you only use half the edges.
Okay.
Then you have another close sequence that also has length n.
Okay,
That only uses half the edges.
that is fine.
And then when you take the union, suppose you have to take the union of him to cancel, but now you have a sequence of length 2n.
Sure, but that will be the job in the proof. So the operations will be join and break. Okay. So consider a closed sequence. With close C1 to CR, increasing heads, length L. So you see L edges exactly in this, and they may be repeating, all that is possible. So if C is not a cycle cover, what does it mean? This happens if and only if a vertex repeats, and so that is possible in two ways. So then some vertex repeats.
It could also happen if
It's not
it's
a
not
cover.
spanning, right?
It's not
Yes.
spanning also. It's not spanning.
Yeah, that is true. So shall we fix L to be n?
Exactly. So if fix L to be n, then you have this.
Okay, let us do that. So length is exactly n. So length of a closed sequence, we fix it to be n, and so in C you see you see n edges, but this is not a cyclic cover. It means that some vertex is repeating. Okay, let I be the largest such vertex. Well, okay, let I be first the largest claw. So let I 1 to R in 1 to R be the largest such that this closed CI, which, so now we go inside this largest claw that is bad, well, not largest claw, but close CI for the max I. Let us go inside this. So say it has k vertices, V1, V2, Vk, and back to V1. Okay, this is the claw, has a vertex that repeats. Right, so either there is a vertex, sorry,
Then, I mean, then we're looking at, then without loss of generality, you're assuming I is 1, right? Because the heads should be increasing.
Right, okay.
So are you assuming that I is 1?
No. The Ci in this, which is not a, so I plus 1 to Ci plus 1 to Cr, that's a partial cycle cover.
That is fine.
Ci, with Ci it is not.
If Ci is not C1, you probably won't be able to write it like this because the clause sequence, the heads are increasing, right?
Okay.
So Ci cannot have V1 as its.
Why not? V1 is not 1. V1 is an arbitrary label.
So
Number is different from
okay,
V1.
so, okay.
V1 is just a variable. The vertices are labeled by 1 to dot dot n. V1 can be anything in that set. Why? No. It's V1. V1 is a variable. It's a vertex variable. V1 is somewhere in Vg, which is equal to 1 to n. Right, so this in particular tells you that Ci plus 1 dot dot Cr are disjoint cycles but when you look at Ci to Cr, that is not. They are not disjoint cycles. Right, this is clear. So why are they not? Why does including Ci violate the disjointness of cycles? Well, either because Ci is not a cycle, or it is a cycle and something here overlaps with some other vertex in Ci plus 1 dot dot Cr. There are two ways. So this can happen in two ways. So case 1 is there exists J prime and J vertices in these K vertices, vertex set, such that Vj prime is Vj. So V1 to Vk are already repeating. So which means that Ci is not a cycle. It is not a simple cycle. Second is there exists a vertex Vj that repeats in later close or cycles. So Vj occurs in so note that both these cases are not exclusive, both the things may be happening. So we can set the convention that first you check case 1 and if it fails only then you go to case 2. So in case 2 when you come then I don't think it will help. We could have assumed that Ci is a cycle, so all these Ci's to Cr are cycles, but there is a vertex in Ci that overlaps, so they are not disjoint, but they are cycles. So that you can think of case 2 as that. And actually no. So this won't be the convention. So convention will be over these cases, pick the least j. We'll go with the least. Okay, so look at both the cases and pick the vertex that is that has the least subscript index j. Okay, so but still what could happen is,
I have a question.
yes,
So we said Ci plus 1 to. Hold on.
We can make make it a single cases, right? Vj occurs in Ci to Cr.
Yeah, but I don't want to do that. In one case I will do join close, in other case I will do break close, break a close, or break into close. So I'll join close or I'll break into close, depending on which case I am in. Well, so you can already guess, right? At this point, so we have, suppose you are in case 1, which is Ci is not a cycle. What do? Can you modify this and get another close sequence?
Yeah, just take away and
Exactly, you break it. Yeah, so you can already guess that case 1 is friendly with the breaking operation. So you break Ci and get a different clo where the number of clos has increased.
If we break it to 2 or
Okay. Depending on how many times we are repeats.
No, so we'll only break into 2. We can fix that. And
these j, right? So there is only one way to break it, even if it occurs multiple times.
yep, right. And case 2, Vj actually overlaps with, say, Ci and Ci plus 1. Right, so in that case you are seeing a connection between Ci and Ci plus 1. So this is a good case for joining. So you join the two with respect to Vj. So you get an associated close sequence. So we have set up an association amongst close sequences that are bad, that are not cycle covers. Right. So this thing you cannot do with cycle covers, but with close sequences you can do this. And so what remains to be shown is that this is actually this partitions the bad close sequences into 2 parts and sets up a bijection with signs opposite. So you can exactly see how things are cancelling out with the sign. Okay, so that is what remains.
So how would we show that when we are clubbing these two sequences,
Right.
the head there is a
Yeah. So we'll see that in the analysis. So now we analyze the break and the join. So let's go to the next page. Just remember these definitions. So in case 1, vertices Vj prime plus 1 dot dot Vj are all distinct because we picked the least j. So before j nothing repeats, right? So we assume, let's point that out. So we assumed Vj prime and Vj to be the same, and since j is the least, between j prime and j you don't see a repetition. Okay, so this gives a cycle. So let's say a sub-cycle. And we can use this sub-cycle to define a new close sequence. By breaking Ci. Into clo1, which is V1 dot dot Vj prime, and where should you go from Vj prime? So the Vj to Vj part we actually remove. So jump to Vj plus 1. Dot dot Vk V1 and clo 2 is am I messing up the notation? Should I say Vj prime comma? Should I add Vj prime also in this? So that is how my notation was, right? Yeah, so clo 1 is V1 to V1 with the subcycle removed, and clo 2 is the subcycle. And everything else, Ci plus 1 dot dot Cr, we are not changing. Okay, so what do we gain with this? Well, first we have to check whether this is a closed sequence. So let us check that. Are the heads distinct? So what is the head of clo 1? That remains the same because we have only removed higher vertices. So V1 remains the min, it's unique. In clo 2, what is the min? Is that the min? It should be J prime, right? We said that J prime is less than J. Okay, you are, yeah, so that is the index. That should be equal to, so how do you show that there is nothing smaller in the middle?
Then J prime would be least.
No, so I don't think I want to say that Vj is the head here. So
Head is minimum by index or
no, the value, the vertex value should be minimum and non-repeating. Should be unique minimum. Then it could be anything, right? So suppose the minimum in clo 2 repeats. I think clo 2 is just a cycle. It's a simple cycle. That is what it should be. That we have already gotten, right? They are distinct, right? So actually this is a simple cycle. So the minimum would be unique. I don't know what it is, it will be something. All I want is now the head of clo 1 should be less than that of clo 2. That is true. Because that is V1, which is less than the head of clo 2. No, I don't want equal to. It should be strictly. So V1 is the unique minimum in C. So because of that. So head of clo 2 is increasing, and well, but there are also these Ci plus 1 dot dot Cr, right? They can be the same.
The head for clo 2 can be in those Ci plus.
Yeah, so we have to show that they are at least distinct, even if not ordered. Yeah, so this cycle is disjoint from the rest. That you would need. So clo 2, cycle clo 2 is disjoint. From Ci plus 1 to Cr. Do you believe in this?
Also, I mean, if it occurs in exactly one of them.
What occurs?
If the head of clo 2 occurs in.
No, I want to prove something even stronger. That clo 2 is actually disjoint from the next.
And also, if it does intersect, if you try to go the other way,
Okay.
if you try to show that if it does intersect, then I mean, you can probably intersect with only one of them, right?
No, I want to show it doesn't intersect. How do I deduce that? I think here I have to use then, if it does intersect, then you will have to go to case 2 probably. Yes, I think I have to switch between the cases.
Can you show what was case 2?
Case 2 was exactly this, that Ci intersects with something else, something next. Ci plus 1 dot dot Cr.
Intersect means just any vertex.
So then you can treat them separately.
There exists a Vj that occurs in, I mean Vj is something that occurs in Ci and also somewhere else.
But then we can
So
treat
when we
them
are
separately.
Sorry?
Then we can treat the cases separately, right? I mean, case 1 if case 2 does not happen. So then
Yeah, so we have to switch between the cases, yeah, so that switching will be needed. So here we can assume that CLO2 is this sub-cycle is disjoint from the rest. So this logical consistency has to be carefully checked, but let me just proceed. So I am basing my deductions on this, that CLO2 is disjoint from the rest, and hence so in the beginning you had Ci dot dot Cr with heads distinct, and when you broke Ci, then you got vertices that are different from V1, and they are different from, you got a head of CLO2 that is different from V1, and it is also different from the heads of Ci plus 1 dot dot Cr. So hence the heads are disjoint. The heads are distinct and you can order them. Look at that flow sequence.
When you are breaking into flow 1 and flow 2,
So we can order the heads. Order the R plus 1 heads. Okay, and okay, what else do I need? So now more important conclusions from this, that weight of C prime is the same as weight of C. That is obvious, because the product won't change when you do these do this break and reordering. What about the sign of C prime? So I want to make this claim that it is the length plus R plus 1, and sign of C originally was L plus R. Is this correct? So I want to claim that if you look at the original, let us focus on this. So if you look at the original close sequence, the parity of the number of even close matches with the parity of L plus R. L is the number of all the edges you see, actually it is fixed to be n, plus the number of close. Why is that? It's a simple calculation. By definition, sign of C is minus 1 to the number of even close. And any ideas?
I mean, we can assume that there are k many of them.
We have assumed it to be R. There are many. Oh, okay, you mean even close. So say say this is even close is E. Okay. And
So that's n minus e times odd.
And let's say odd, yeah, so number of odd is then r minus e, okay.
So,
Either odd increased or even.
and the total sum of all these edges would give me n. And then, I mean,
Okay.
times some
Mhm.
even numbers. So if we go mod 2 on both sides, I think.
So if you look at this Ci size for I equal to 1 to r, this is equal to L. So L is equal to sum of the sizes. So if you go mod 2 now,
So the even part just cancels.
Even
so
part-
minus e times.
right, and the odd part gives you r minus e, which is also equal to r plus e, well, which implies that L plus r mod 2 is the same as e. That's the proof. Right, so sign of the original closed sequence was total number of edges plus the number of close, and in the same spirit sign of C prime is total number of edges plus the number of close, which has increased. So the parity changes, it flips. Is that clear? So that's a good process.
So this breaking into flow 1, flow 2, yeah. So doesn't it make the potential case for case 2? So Vj prime is occurring in now in flow 2. So
What do you mean?
so isn't this breaking into flow 1 and flow 2?
No, so we are done with this process. We are now looking at C prime, which has one more with the same amount of edges.
Even case 2 does not happen. And then when case 2 happens, we can keep it separately. If case 2 does not happen, then we are done with it.
Right, so we set the convention here that if both cases are applicable, then use case 2. Okay, this is just a convention to break the tie. So since we are breaking the tie, we can assume here that the disjointness, because otherwise we will be using case 2. Yeah, so there is some logical stuff you have to check so that we are not in a vicious cycle, but I think it is fine. So let's now quickly do the join operation in case 2. Case 2, we have this Vj which is in Ci also appearing in Ci prime for I less than I prime 1 to r. Okay, and this I prime is unique. Right? Why is that? No, it's not because of that. It is because Ci plus 1 to Cr are cycles. They are disjoint cycles, yes. Oh, you meant for the I, right? Yeah, so the way I was defined was largest I, such that you get a bad close. So after this, you only have good close, which are all cycles, and they are also disjoint. So when Vj of Ci, vertex Vj of Ci reappears, it can reappear only in one place. So that is Ci prime. So now, since Ci and Ci prime have this connection, we will just use it to join them. So in this case, the number of close will fall by 1 with the same effect on the sign. No, don't break. So here we join the close.
Now the flexibility of the definition of flow helps.
At the vertex Vj to get flow Ci prime. Yeah, so this we have to write as a sequence of vertices. So let us, so we are filling inside Ci, so Ci go up to Vj, V1 to Vj, and then you can take a detour inside Ci prime. So follow the map inside Ci, the cycle Ci prime. So that would be Ci prime minus Vj part vertices, right? So break that cycle by removing Vj, put all those vertices in that order here in this place. And so why Vj plus 1? Well, because we have removed the first Vj in Ci prime description. So it will come back to Vj, and then from that you can proceed to Vj plus 1 dot dot Vk V1. That is the description.
You write Vj first before Vj plus 1.
Sorry?
Ci prime minus Vj will exclude Vj both at the start.
Yeah, so let's say it removes from the first, because that we have included.
You can just write Vj.
Or we can just write Vj minus 1, yes, that is true. So from after Vj minus 1 you go to Vj in Ci prime. Think of Ci prime as headed with Vj. So Vj is the first, then it will complete the cycle, come back to Vj, and then move to Vj plus 1. That is the order. So think of this representation. So all the edges are available and you can do this close walk. Starts and ends at V1. Okay, and with this call the new sequence C prime. That's the new close sequence, which has now one less clo. No, so we have to now do those checks, right? Is the head, what is the head of Ci prime?
The head of Ci prime is same as head of C.
Right, so that is because the Ci prime that we have put inside, the C of I prime that we have put inside Ci, that these are all higher vertices. So V1 remains the unique minimum. That is good. And the heads are in the same increasing order, because we just deleted C of I prime. So delete C of I prime and then the head sequence is the same. So heads are distinct. Okay, so this means that it is a valid close sequence. So that proves that we can call it a close sequence, and then we can talk about weight and sign. Well, so weight of C prime is the same as weight of C because we have not lost any edge, neither have we added a new edge. Sign calculation is the same as before. So sign of C prime is minus 1 to the length which has not changed plus r minus 1. Sign of C was opposite. Is that clear? So sign has flipped, weight remains the same. So it is now fair to say that the above description gives a map tau from closed sequence set of G minus cycle covers in G to itself. Right, so this is defined only on non-cycle covers, because otherwise you won't be able to get into case 1 or case 2. And from such a from a bad closed sequence, you are only going to a bad closed sequence. You cannot go to a good, you cannot go to a cycle cover. So it's a map to itself, and additional properties are tau has no fixed point. Well, obviously, because it is changing the number of close, so there is no fixed point. It doesn't fix anything in this set. It moves everything, it flips the sign, flips the signed weight. It only flips it, it doesn't change it by any other way. And but you need one more thing, right? You need for bijection it should be invertible. So why is that? Well, because it is a finite set and we have defined tau on everything. So with these three properties on the map, tau is actually partitioning the set into two halves and moving anything from the left to something in the right. And when you apply it again, you come back to that. Okay, so these are called involutions. So tau is an involution.
Set of okay, we have fixed length, close of length at most n.
No, exactly n. So it's an involution, and it is moving everything.
Why is it invertible at this point? Why is it injective?
Because it is.
You won't get two different.
Why can not two things map to the same point?
I think because the.
There is no fixed point property, yeah.
No, that doesn't. That. No, mapping. No, everything gets mapped to something, right? So if two things get mapped to the same thing, then something remains unmapped, and that is.
Or you can just directly show that tau square is identity.
Exercises are the same, right? It's from it to itself. So if two things map to the same thing, something else would have to remain unmapped.
Yeah, so by finiteness, I think it is already there. But also explicitly, you can see that if you apply tau again 2 times, so basically you break and then so then it will be breaking and joining and get to the same thing. So it's actually on every instance it's an involution. You can check that. So yeah, so no such loophole is there. So this is actually leading to a cancellation. Okay, this leads to a genuine cancellation term by term. So one term gets cancelled with its negative. It's the simplest form of cancellation. So overall we get this property that if you look at the signed weight of cycle covers, closed sequences of a graph, then it is the same as all the bad things cancel and you are left with cycle covers. The strict subset, proper subset, and that is by almost by definition it is determinant of the adjacency matrix of the graph A. So that finishes the proof. Is that clear? That finishes our theorems, our lemma. This lemma is shown that determinant is equal to sum over closed sequences, and now the question arises, so this is a mathematical fact, but how will this be turned into an algorithm, right? So from one exponential sum we have moved to a bigger sum. Now how can this ever help you in life if you make your sum even bigger?
If like there's a recurrence sort of something like you said.
Yeah, so the term is dynamic programming. So using dynamic programming you can actually implement this huge sum on cycle cover, on closed sequences. So going over permutations is impossible in an efficient way, but magically going over the closed sequences, because closed sequences are so relaxed that this thing you can actually implement using dynamic programming. I don't think we have enough time. This we will do in the next class. It will have a short proof. Well, dynamic programming itself would not have been enough for our purposes. We will actually do it systematically in the form of just matrix multiplication or ABP. We will just directly write down the ABP which computes every path of which computes a closed sequence. Yeah, let me write down the statement first. So ultimately what you will get will be very powerful. So this expression has a nice implementation. So expression 1 has a width n square, depth n plus 1, ABP, where n is the number of vertices equal to the dimension of A. Yeah, so you can think about this implementation, why this thing why expression 1 can be written as the, oh sorry, I am pointing to the wrong thing. Closed sequence. Yeah, so the definition of a closed sequence is so relaxed that you can walk in a nearly memoryless way. So all you have to remember is the head. So you just remember what is the head above which you are allowed to visit vertices, and just continue to walk on that. At some point you decide that you want to close the walk, so you close it, and in the next step you move to a bigger head, creating a new flow. Okay, so this is what a path in an ABP will do. So every level will correspond to in every level of the ABP. If you think of the levels, there is S vertex, there is T vertex. So, and these will be the vertices. So, the depth will basically represent these edges which you are picking to walk forward. So, that will be, so as you go along, pick edges, pick an edge to walk on. And yeah, to implement that in a level, you will need vertices around n square. So, this will basically n square because you want to remember the head and you want to remember the current vertex where you are sitting. So, these two things, it's basically a tuple, right? Head comma current vertex, it's a tuple. So, the values that this tuple can take is n square. So, this within a level, the number of values is n square. So basically this is what is your memory requirement. Yeah, and then based on this we will implement. So, number of edges gives you the depth, and the number of possibilities of head comma current gives you the width. So, it will be an n square cross n ABP. Okay, so, we will finish this tomorrow.